So we're going to get going. I just changed, hopefully nobody worked ahead on lab 3B because I just changed it. And we're going to cover linked lists today, linked nodes. I'm wondering how many people had problems with the array algorithms lab. Anyone want to talk about anything? The last part, you mean the challenge problems?
No, not yet.
Which was the replacing? Is that where you're? Oh, that's assignment, homework one, yeah. Homework one is due on the 18th, I think, right? Yeah, so. But the array lab, anybody else have any anything you want to share or any? Uh-huh. Yeah.
Would run again. Would put the next to last element in the last element of the array. For somebody would copy those two. Oh. So my remove stuff is stopped working.
Okay.
And I put that on my comment when I.
Interesting. I'll take a look. This one I didn't have give you a lot of support for this, but maybe sometimes I give too much support, so that maybe makes up for it. Question in the back, yeah?
Yeah, I was having I just couldn't figure out how to do, like, if you're trying to get rid of one duplicate instead of all of them. I couldn't figure that out for the last one on that question.
Well, I added an extra slide based on some questions I got. I know a lot of people got hung up with the remove. And what I want to emphasize more than anything is that I think as you're still relatively beginners, and that means you're used to probably starting to code without really understanding what you're trying to do. And one thing to remedy that is to start getting into the habit of diagramming stuff really well. So I added a slide here just to kind of, oops, I think that's here. Here we go. Yeah, so, removing an item from an array. I gave you some notes here. It says, copy all the items. So we're trying to remove, say, the 56, right? Copy all the items except the one you want to remove into the new array. You'll have to shift some items over one to fill in the gap. That's a really general statement. It's true, right? You know that because of that. But how many people actually drew that out to kind of show an example and kind of help guide their coding? Yeah. Sometimes you think you have it in your head, but it can get mishmashed, until you actually lay it out on paper. It's really not often clear. So I encourage you to get into the habit of doing a precise example before and after. And I'll be feeding you some of these things later, but I expect you to kind of be able to do this on your own. And this is an example of, I just want to do this slide. Big, no, that's not it. I guess I can, oh, there we go. And how do I hide this thing? Oh, that is so annoying. Just move. Now there it goes. So here's an example, right? And it doesn't take much to just come up with a simple example, have an old array with some numbers in it, a new array, and this is the target that we're trying to remove. And you can kind of see that there's two types of moving operations, right? And so what I've been suggesting to people is that you think about doing this with two consecutive loops. So you can have one loop where you are copying the items directly into the same spot from the old array to the new array. So that would be something like new array square bracket I equals old array square bracket I, but you got to put that in a loop and you just copy them directly. And you do that until you hit the one that you're trying to remove. Right? And when you find that, so you're going to need a while loop that terminates or a for loop that terminates when either you run out of past the length of the array or you hit the item that you're trying to get rid of. That's you have to express that as an and though, right? Remember we talked about that logic, kind of weird, the for loop for k equals 0, k less than, old array dot length and k not equal to target, or I mean, old array square bracket k not equal to target. As long as both of those conditions are true, then you can kind of keep copying things over. But when one of those, either you fall off the end or you find the target, you stop. And then you can start a new loop where you continue from where k left off, and now you're moving things over one. And that would be something like old new array square bracket I minus 1 equals old array square bracket I. And you set up your next loop to kind of continue until the end. And that's how you paste over that one that you're trying to get rid of. Until you do it so that you can clearly see it's really not that complicated of an issue, people generally get tangled up in just really fuzzy things that then lead them down strange pathways. So this is a way to just bring clarity in what you're doing. And I'll be giving you some of these things, like I said, but I hope you learn to do it, and especially in the topic that we're going to do today. It's really important to be able to start doing it. So plan on pulling out a piece of paper while you're doing today's lab so you can really look at what you're doing and get some perspective on it. It's really important. Okay, so I just updated these links. So if you had your thing open, you might want to refresh it. This is the link to the new lecture. And we're talking about linked lists today. And I think it works better if I download this, so I'm going to download it. And while we're at it, there's a new download, which it's still called Lab 3, but it has the Part B stuff in it, whereas last week it didn't. So you can grab this thing here. And open it. And extract it and put it in your normal working area. Now you might want to name the old one Lab 3a or something so you don't get them mixed up. Like here's my old one. Before I paste the new Lab 3 over, because you don't want to accidentally erase your old work and everything, what you call this lab, your old lab, you could call Lab 3a. And then you can paste the new lab in and call that just plain old Lab 3. And this lab will have some extra files in it, as shown here, and it should compile. And what we're going to be doing in this lab is the same thing we did in the array lab, only instead of using an arrays, we're going to be using linked nodes. So the same problems are in there, but you're using a different representation now, and it's going to be challenging. It's going to be a little pretty weird. But you kind of got the familiar of how you do things with arrays. Now you're going to do the same thing with linked nodes. And it's kind of a good compare and contrast thing. And it's a new domain. Everyone's going to find this a little bit unsettling. So we're going to talk about how nodes can be used to store data and what a node is and how you can chain them together. And then we'll go through some examples of some basic operations. So we'll do this interactively together. This one we sort of need to do interactively because it's really hard to get the hang of it. until you've just gone through it a couple times and seen it. But a linked list gets around the problems with arrays. We talked about those earlier. Anybody remember what were some of the problems that we have with arrays, or why arrays are not the best thing always? What were some of the cons of working with arrays? Yeah, the size is kind of stuck, so you got to allocate more than you need or whatever, and then reallocating stuff or expanding the size of an array occasionally is going to make your program kind of halt a little bit or slow down while it does the copying kind of thing. So linked lists are very uniform. You basically have this common elemental data type, which is a node, and the node contains two fields, a data field and a next field. And you chain them together. The last element has a reference to null, which is just indicating that you've reached the end of the chain. So the node class is pretty simple. This is how the node class could look. This is a node of objects, and we have a data field and a next field, right? These are the instance variables of the node. And the constructor just takes a data element and a next reference and assigns that to the internal variables. It's really straightforward. So here's some code that creates a linked list, and I think actually we're going to get away right away into just doing some of this hands-on because it's a little bit hard to follow a lot, I think. But what you do when you create a node is, like for instance, this cat node is going to be a new node with the word cat in it and a reference to null. And you can sort of visualize this like a reference variable cat node that has a reference to this object, which has this variable value data cat and a reference to null. And then you can make another node called bat node, which has the word bat in it, and it has a reference to the cat node in it. So that reference, we've been drawing these reference variables all the time as arrows. It's sort of like pointers in Java. Bat node is a reference to bat node, but then when we construct the bat node, we put the reference to cat node in the next field. That means the next field, this is the next field of the node. It has a reference to the node that has cat in it, right? And then you can do that with ant node and make ant node point to bat node, and then you can make head point to ant node. So you're kind of constructing this list backwards with the last item first, maybe a little bit like a stack. But that is the code that creates a linked list. Now, maybe it's good to just do this as a lecture, and then we'll do some of this stuff kind of working in as a demo. Because it is kind of nice just to look at it. You've seen it, right? So, oops, I didn't want to do that. Hide that. Okay. So when you say head.data, head is a reference to the object which has the ant in it, and the data field is a field that contains the word ant, right? So you say head.data, and that prints out the word ant. If you say head.next.data, this is the next field of the ant node, right? So head.next is a reference to this guy, and then this guy is referring to the bat node. So then if you then access the data field, you're going to see the word bat, right? And you can see how you can keep chaining these together. You can say head.next.next.data and head.next.next.next.data to get the other two items. And it's showing you how you can go through the chain and access these different fields. And it seems cumbersome when with an array you could just refer to an index and get the value there. Here you kind of have to chain things together. Yep. Yeah, we can do a for loop too. But these are the basic operations, and then we're going to make it work better for us by using loops and other type of code to make it repeat. Yeah.
Oh, fuck, sweetie.
Sure. Yeah. Yeah, you can do all that. So as an example, here's a loop right now. And so to actually traverse a list, you need something equivalent to like a counter in a loop. And what we use for a counter is another reference to a node. So if we say node p equals head, I'm going to make another variable called p, and it's going to point to something. What's it going to point to? The first thing, which is what? End. Good. A lot of people say it points to head. But what happens is, you know, head holds a reference, and what is in that reference? What is that thing really that head holds? A data? Of what kind of data? But head, no. See, the string is over here, right? Well, what's in here? What is that? It's a reference to and. What is a reference? A pointer. And what is a pointer? A location in memory. Yeah. It's holding an address. And what is that? It's a number. It all comes down to numbers. Eventually, it's a bunch of patterns of ones and zeros, right? But they mean something. They mean where you're going to find this object in memory. And that is what's stored in reference variables. And next is a reference variable, and the data field is also a reference variable. To be accurate, actually, I should really draw. You know, with strings, we kind of sometimes just draw them in the thing that they're the reference variable. But in truth, a string, you know, a reference to a string is a reference to a string object that has the word ant in it. So I should actually have the ant, the bat, and the cat, the bat, and the ant outside of those things as well with arrows. But for simplicity, we kind of just store them in there just so we don't have too many arrows on our display. Java has references for all objects. Every object variable is a reference to where that object actually is. Anyway, I digress. Getting back to this traversal, we have this reference p, which is referring to the first node because p equals head is copying the address from head and putting it in p. And we can say while p does not equal to null. What does that mean while p does not equal to null? If it's not empty, what happens when p equals null? Sorry? It kicks out of the loop, but what would that signify when p is null? We got to the end of the list. Why? Because the next field has a null stored in it. That null is ultimately a number, right? And that number is probably 0. Kind of what null is. It's just usually 0. But it means the end. For us, it means the end of our chain. So when p equals null, that means p got to the to the next field of the last node, and we're done. But if it's not equal to null, we can print out p.data, which in the current diagram, what would p.data print out? Right now, where p is pointing, what's p.data going to print out? Ant, right? Because p is a reference to the node that has ant in it, right? So it's going to print ant and an arrow, and then it's going to say p equals p.next. When I say p equals p.next, what do you visualize happening to the diagram here, where the data field is the first one and the next field is the second one? When I say p equals p.next, how does that change? P moves over one space. How did you know that, Sean? Because you took C++. Lucky guess. Yeah. But yeah, if you've seen this before, so p equals p.next, it's really not that hard to imagine. Well, next is a reference to the node that has bat in it. If I say p equals p.next, I'm taking the number in here, which is, what is that number in here in the next? We just talked about that number is an address, or a memory address, a number that refers to where you can find that thing. So I put that in p, so I would have to kind of redraw my diagram to make p now refer to there, right? So that's all I do that. And then p is not equal to null, so I can print out p.data that prints out the word bat and an arrow. And p equals p.next again is going to move p to the cat node, so I can print out cat. And then p equals p.next one more time is going to put a null into p, right? When p has that null, it means we got to the end of the line. So that's how you can traverse a chain of links. And you can make a method that does that as well. Print list method that just prints the whole thing. So again, the last element is called a null link, and you can manipulate the individual elements, and you can also manipulate the links. Linked structures allow a lot of variety for how you can represent things. You can have a sequential set of nodes. You can have a circularly linked list where the last item refers to the first item. You could have a cyclic list where the last item refers to one of its predecessors. So you can have a lot of fun with chaining things together in different ways. Getting back to this idea of a memory address, though, in this diagram, I've added the memory locations to kind of help show you what that actually means. So if you imagined that the ant node was stored at memory location hexadecimal 420, the X sort of refers to hexadecimal format. And what does that really mean? That means, you know, if you think of memory as a huge giant array, then, you know, if this is the index hexadecimal 470, then right here is where the object is actually stored. And let's just sort of draw the ant here and this reference to 286 here. This is all at some point symbolic, but you get the idea, right? Now that 286 means that the next node is going to be at location 286, so you might have a 286 over here somewhere, and you've got the word bad in here, right? And a reference to 504. In fact, you can use an array to represent a linked list, and that might actually be kind of a fun thing to do. Maybe you should do that sometime. Because that would really sort of drive it home in a way if you made an array that had, but anyway, some other time. So this 286 means if you're going to find the next node, you got to look at memory location 286 to find it, right? And there you have the word bat, and then a reference to 504, which is where you're going to find the last node, which is way down here. And the beauty of this is that the actual order of, you know, the locate of where you're putting these things doesn't really matter with a linked list. So any available space that has room for a node could be suitable for storing a node, regardless of where that space appears in the order of the other nodes. It's just a matter of the order in which they're chained together that counts. So, questions? Okay. All right, well, let's start doing some of these things. I think the demos will help clarify some stuff as well. Once you get your hands on these things, it makes it a little more straightforward. So let's look at the demo code. This is the demo app. Here is the node class that we talked about in the slides, the data field, the next field. And the data field is an object. So we're now going to look at here and activate, well, demo one looks like it's active. We're creating a list of 3 nodes the same way we did it in the slides. And you can print the nodes directly like so. And let's go ahead and run that. There they are in order, and looks like item 6 is active, so maybe we can just comment out 6 for now, taking away that slash. Taking away the slash, there we go. And this would get the last item. Well, actually, that would get the null. And you'll see what happens if you activate this code now. You're going to get a null reference error because we're actually pulling out that last node, which has a null in it. And if you try to print the data field when next contains null, it's like you're saying null.next. And of course, there isn't a next field with null or data, null.data. There is no data field with null. Null is just like a 0. So that's why you get an error when you do that. So you can put this causes a null reference error. And as we saw, you can print out all the items safely with a for loop. So you can say, or a while loop, you can say node p equals head, start p at the beginning. And while p is not equal to null, we can print out, or just print, not print line, just print p dot data followed by some arrow in the display. And then you can print out, or then you can let p equals to p dot next. So this is print the data field, and then advance p to the next node. A few comments there just to kind of explain what's going on with that stuff. Okay, and you can try that out and make sure that works. Make sure you comment out the line that caused the error, so it's not being used anymore. And oops, there's the first 3 items. And then just to kind of end that gracefully, we could just print out a null afterwards. So we can say system out print line null. It's really just a just a decoration, really, just to kind of indicate that we hit the end of the chain. So we'll print out if you want.
Results, it was bad cat and no, it was okay to have that null at the end.
Yeah, it's not a null reference error to print out the word null, right? We're just indicating that this is the terminator symbol of the chain. You don't have to print it out if you don't like it. That's totally optional. I'm just sort of you're going to see this in the drill exercises, and just know that sort of means you got to the end of the list. And it turns out, why reinvent the wheel all the time? Put that in a method, and this is what the print list method does, just to printing out all these things. So you can call print list and just pass it the beginning node of the chain, and get another copy of the output. Just call print list of head, and you'll see another copy of that printout.
So pretty much this will be commented on, right?
Well, you mean after we finish? Mm-hmm. Sure. Since you already got a copy, you can comment that out if you want, just so if you don't have two copies. Yep, that's fine. But keep demo 1 active because demo 1 is where the list is actually created. So now we can play around with inserting a node at the beginning. Now, again, since this is new for many people, let's think about what that means, how to actually do that. And oops, I need to find a real estate is really tight here. I'll find this guy. And here's the code to insert a node at the beginning. If you make a new node and assign it a reference to a new node object with some data, and then you let new node.next equal head. What does that do? It makes the next field of new node, right, refer to ant. Y'all agree? So that you now have sort of two references into this chain, but head is no longer referring to the front. So to fix that, you can just let head equal to new node, and now head is going to be referring to that node that you just created. And do you think order matters? Can you flip the order and do head equals new node first? What happens if we do that? You know, we would create the new node. Suppose we did, I mean, right now we're doing this as 1, 2, and 3. What if we did step 1 and then step 3? What happens when we do that? Yeah, you would lose the list because, yeah, right now, if you let head point to new node before you actually change the next field of new node, what you're going to end up is you're going to have a list that just has the first node being the one you just made. Everything else is gone. So you have to be careful when working with lists to make sure you know what you're doing. This is why pictures can really help. If you draw a picture and you can kind of connect things as your code says, you'll start to understand what's going on with your code in a way that works better. Yep. Instead of, sorry? Oh, yeah. That's a shortcut, right? Good. Glad you asked, Katya. So you could combine steps 1 and 2 together, right? And if you just put head right here, when you create the new node, you can initialize it with a reference to the first node of the existing chain. Yeah, good point. I was going to say that and then I forgot. So that is another option, and either way is good. I think I initially kind of go slow to show the steps sequentially, because you don't want to pile too much in there, but you can do it if you want in 2 steps instead of 3. So we're going to let new node equals a new node with asp and null. If you want to do it the long way, you can do it that way, or you can put head there. Either one of those is good. And then if you did it the way I'm doing it, you can say new node dot next equals head. And head equals new node. Okay, and you can print it out and see if the new item got added, and it sure did. So that's how you add something to a chain at the beginning. Everyone okay? Any questions? Well, that's when you're inserting at the beginning, and that's relatively simple. Inserting a node in the middle is a little more tricky. Inserting a node in the middle means, well, let's see here. You have to make previous node point to the node before the insertion point. So create a new node and set new node.next to refer to the items after the previous node, and set previous node next to refer to the new node. So here's an example of previous node equals to head.next. Well, here's head. Head.next is the ant node, right? So we're going to call this previous node. And then we make our new node with some new item inside it. And it's already been inserted in there, but we can sort of draw it initially. And then we're going to set new node.next equal to previous node.next. Okay, well, previous node.next is a reference to, before rat was in there, it's a reference to bat, right? So it was going here. And previous node.next equals new node. Well, is going to, well, new node.next equals previous node.next means new node.next, this guy here, is going to get the address of previous node.next, which is the address to the rest of the chain, right? This is the rest of the list is assigned to new node.next. And then previous node.next is then going to refer to new node, meaning that's when it refers to the rat. And again, order matters, right? You have to do it in this order, or you could risk losing everything that comes after your previous node. So we're going to let node. Oh, first we have to advance. So we have to define node before or previous node. We can call this node before equals and dot next. Step 2 is we make a new node. And again, you could simplify this by combining 2 steps, but let's just sort of spell it all out, and then you can kind of, if you like, oops, you can make it go shorter. So we can say new node. Step 3 is we got to set new node next to refer to the items after node before. New node.next equals node before.next. So node before.next is a reference to all the nodes that come after the current node that node before is pointing to. and node, then we finally let node before dot next refer to the new node. It's now safe to bring that one in because everything's been linked up with the new node properly. Got to activate that code. Okay, so compile and run that, make sure that works. I already have a new node, so I can just not redeclare it and just say new node equals new node. And now we have this extra item in there. So that was how you do an insert. Any questions? They're actually kind of fun, right? It's you're playing with a kind of a structural thing. You can build in any order. You know, it gives you a lot more freedom when you're working with nodes than you do have with arrays. So yeah, you'll enjoy it. What about removing a node? So if you want to remove a node at the beginning, well, here's a way to print stuff out. We've already kind of seen that. And oh, actually, this is a kind of a comparison between printing out linked chains and arrays, right? So you can set this current equal to the front, and well, it's not equal to null. Print out the item, and then advance the reference. And here's with an array. You know, you know you're going to have to go up to length and print out each item, and then add 1 to I. That's sort of like advancing the reference to the next node of the chain. I think I maybe should rearrange these a little bit. So the yeah, so in summary, you know, an array has, this is sort of a list of the differences between them and similarities. Arrays are a collection of elements of the same data type, and so are linked lists, but they're connected by pointers. Arrays have a fixed size. A linked list can grow and shrink as you need to. Indexing an array is much faster than indexing a linked list because you can go straight to the item that you're looking for with an array, right? That's the index just gives you a arithmetic offset, and it knows how to find the items really fast. Traversing a list for the desired value is slower. If you're going to insert and delete, you have to shift items just like you had to do for the remove and insert for the arrays. But you'll find that with linked nodes, you can create a new node and just link it in really fast, so it can be faster. And you can make different types of arrays, one-dimensional, two-dimensional, or multi-dimensional. And you can have singly, doubly, circly, and different types of lists like that. So one thing about pointers, though, you have to be aware of, if two variables contain reference to the same object, that object can be modified using one variable's reference to the object, and then altered. It will alter it from the view of the other one as well. So aliasing is something we've kind of explored in the past. If you have an X and a Y that are referring to the same object, you can change one of these fields using X, and it will also show up in Y because they're intrinsically related to the same thing. So it's just something to be aware of, and pictures will sort of help clear that up when you do run into weird situations like that. But to remove a node at the beginning, you would basically, it's quite simple. You would just advance head to the next node in the list, and then the unreferenced node will be garbage collected. That is That is one thing that happens with Java that's kind of nice. So if you advance head using head equals head.next, head is going to now refer to that node. You then have a node that has no references to it. That means no programming variable or anything can access that data anymore. And so it needs to be reclaimed so that it can be reused. And there's another program that kind of runs in the background that goes and looks for these types of nodes. And when it sees them, it deallocates them so that something else can use them. Remove node at the middle, again, you have to make a previous node to point to the one before the deletion point. And if you say head.next, it's going to be pointing to here. And then set previous.next to the list following the deletion node. And then you can rely on the fact that the unreferenced node, again, will be garbage collected. So previous node.next equals previous node.next.next has 2 in a chain, right? So that means this reference is going to get the address in this reference. So in other words, rat will then point to cat. And it goes away because the garbage collector grabs it. So let's do those two. Yeah, this will be demo 3 and 4, I think. Demo 4, I guess. So advancing head to the next node. So we just say head equals head.next. And that gets rid of that first node asp so that we start with ant again. And then we can continue with the next one. Looks like the code's already done here. So we set node before equal to the node before the one we want to remove, and then we skip over the node that we're going to eliminate. So you can see the node bat is removed. Any questions? Should I walk around? Finally, you can modify a node's data. And that's basically just changing the data field to something else. So pet.next.data equals pet, going to pet.next.data equals pet. Like so, we'll change the second node to pet and print that. So now that has become pet. And then just for fun, you can try to add and remove a node after ant, which should not be too hard to play around with that. I don't need to see that. That's just sort of for fun. That will pretty much wrap up the lecture lab demo. And then you can work on the lab problems, which are taken from the same problems that we did last week in arrays. So if you click on the instructions here, it should bring up the new, but it looks just like the array one. So you can try to find a way to sum all the elements in a list. You know, you can write methods to do all that. You're going to have to traverse the list and do the running sum that way. Just working with lists instead of arrays. Most of these will be not too bad. Then you have the remove and the insert, which aren't so bad either. Replacing the item at the end might be a little challenging. And replacing an item at a certain position could be a little interesting, but not too hard. And then again, if you want to try to do a shift, that could be a little more challenging. That might be interesting to sort of make your list circular if you want to do a shift and just advance the head pointer, you know, where you want it to go, and then it sort of looks circular. And then it sort of looks like it has moved. Yep, question? So no, you're going to do all this in the linked list algorithms class. Now I realize because we were working with numbers last week mostly, that whereas the node class represents the data field as an object, it's more cumbersome to do that. So I made a new node called int node, which represents the data field as an integer. So the int node works exactly like the node, but it holds integers instead of references to objects. And you can do everything with that int node class, and we can kind of get started together if you want. I also want to point out that, yeah, there's going to be a lot of drills, and these drills are pretty good. Some people have mentioned them already, that they were a little puzzled by the second half of the drills. Now that you've seen this lecture, it might make a little more sense, but you can kind of see here are some statements that have been written. So for each one of these, you're going to want to like sketch these out on paper, drawing these things on paper. All that kind of activity will be really helpful to visualize what's going on with these different statements and how these statements are going to change the order of the items, change the structure of the list. So these are really great exercises to practice working with these things. And this is sort of a graphical representation of a linked list with a bunch of pointers to it. So if you're all unclear, this should be a very helpful activity. But let's go back to the lab and look at this. The first one we're going to do is the sum one, right? We're going to have to sum all the elements in the list. So let's look here in the linked list algorithms class. Actually, it's kind of interesting to see the list being created. I actually, it's a little cumbersome to create lists, so I started with the original arrays from last week and then made lists. And then we are passing the arrays to a method called createList, which does the creation for us to make it a little bit easier. At the bottom here, you can see the definition of the createList method. It takes an array of integers and then makes a new node and a node pointer and traverses and creates new nodes along the way. And then when it finishes, it returns a reference to that list, which can then be stored for later use. So here's the sum method. And the sum method is going to want us to add up all the items in the list. So we can make a result variable, which is 0. And you can make a node traversal reference or pointer called P if you want, which is going to initialize to the first item in the list. So how are we going to refer to the first item in the list inside this method? List. So list is receiving the argument from the call to sum, which is here. We're saying sum of list 1. And so list 1 is being passed to list, and list 1 is a reference to the first node in the chain. By the way, I also made a toString method so that we could print a little descriptive message before we actually print out these things. So the toString method turns a list into a string. You can kind of see that down here, initializing P to null. I'm not sure why I did that, but I think I just did it just to be safe. It's a good idea when you create a list variable or a reference variable to a list to initialize it to null, just to be safe, so in case you forget there's a null in there. Although actually it's not that big of a deal, because in Java the default value is null, but in C++ you can get some crazy numbers in there and really mess you up. But you make a string result, and if the list is empty, you're just going to return null, which means there's nothing in it. If the list next item, in this case, if the list next item is null, that means there's only one item in the list. So just return a string with just that one item's data. Otherwise, you're going to make and traverse the current list and add the data field and an arrow, and then at the end you can tag on a little null if you like, or just delete that if you don't like the null, and return the result. So node P equals list is going to start P at the beginning. Yes, it does. I'm going to screw that up, and you probably will too. You have to say int node now, even though we've been saying node all the time. It's an int node. You'll get all these errors if you don't. So you can make a for loop also that traverses all the items. You can see here is a for loop that makes P look at every item in the chain up until the last one. So while P.next is not equal to null, what's the significance, by the way, of saying P.next is not equal to null, as opposed to P not equal to null? What's the difference? If we stop when P.next is null, how does that differ from when we stop when P equals null? Well, if you stop when P equals null, it's a difference of basically stopping the loop after you've looked at all the items, or stopping the loop when the node pointer is pointing to the last item. So in this case, I wanted to not have a hanging arrow displaying at the end of my data. So I make it stop one earlier. So P.next is not equal to null. But if you're going to do most of the loops here, which have to look at every node in the chain, you're going to want to do it until P is not equal to null, or while P is not equal to null. So when P equals null, you stop. I think I should just let you work, and then I will come around and see who I can get sorted out. So you're going to just turn in the list algorithms.java file, or linked list algorithms, sorry. You don't need to turn in node.java. Storesim.java is going to be done on Wednesday. And then I had this funny, I guess this is sort of a funny creative challenge. I don't know. Do this though in the linked list if you're going to do it. The idea is to create two chains of 100 nodes that both end in the same last node and prove that they are the same by printing the address of the last node in both chains. So I just thought, well, you know, some people were looking for a challenge, and it's interesting to think about a structure that would look like, you know, or what that would actually look like, right? That would sort of be like a converging of two rivers. So you would have, you know, like 100 of these guys in two parallel paths, and at the very end, they're referring to the same last node. I don't know why you'd want to do that, but see if you can write some code. If you're interested in that, see if you can write some code to do that and demonstrate that they share the last node by showing that the address of the last node is the same in both chains. Mm-hmm. So the question is, why do we have to do a node before with these things? Why do we need a previous node? And the answer is, you know, if you really want to get rid of this yellow node here, you have to change the structure of the list so that the node that was pointing to it is now pointing to the one that comes after it, right? So the only way you're going to be able to do that is by pointing to the previous node, because that's the node at which you can access this variable, the next field, in this node, so that you can redirect it so it points to cat. Yeah. Could you skip over 2? Yeah, you could. You could say previous node dot next equals previous node dot next dot next dot next, and then you'll skip over 2. If you want to delete 2, that's how you would do it. Yeah, good questions. Any other questions? Mm-hmm. Okay. Oh, you got an infinite loop going on? Okay, let me see. The question was, in our examples here, we use the word head. And when you look at the SLL demo, the first item of the chain is called head. But what is head? Head is a variable, where are we here? Head is a variable that holds the address of a node. Okay, well, when we create our linked list here, I didn't think it was, I think it made more sense instead of calling them head 1, head 2, head 3, although you certainly could have. I called them list 1, list 2, list 3. So these variables are getting a reference to the first list is making a new node. So basically, this is a reference to the first node of the chain, which is the same thing as head. So list, a variable called list is a reference to the first node, just like head is a reference to the first node. So when you're writing these codes, methods, you don't, if the method is written like the sum, where the parameter is called list, you're going to have to use list for that. If you don't like list, you can just call it head right there, and then it'll work the same way. So, ideas. So again, that remove method is going to be a little tricky. So I think with the with the remove method, you want to search for the item that you're trying to remove, and you want, when you're finished, maybe it is p.next.data. You want the node before the node that has the thing you want to remove. Yeah. So p.next.data, when p.next.data equals 45, you should get out of the loop. So p stays at that location. So and maybe p.next not equal to null. But then once you get out of that loop, then you can maneuver the pointers. Yeah, it's going to be something like that. As your condition, and then advance p. And so when you finish, then you have to sort of figure out, that I finished because I ran out of list or because the target is where it's in the next item. Remember, the remove algorithm is about locating the node that becomes before the one you want to remove. So a while loop that will navigate p to point to the node before the target node is the first step of the loop. So that's basically step one. If you can first just focus on just getting step one to work, that's actually probably the hardest part, because step two and step three is, or step two is actually quite easy. But now, in our example, in the demo, we only, we got a really simple one where we could just put it in some planet in some location and just rearrange it from there. But in the remove method that we're doing in the lab, it's step one is really where all the meat is. So basically, you need to come up with a way of navigating P so that it's so something like this, where while p.next.data is not equal to target, because when p.next.data is the target, you want to get out of there, so that p is actually sticking there at the node before the one you want to remove. But you also want to make sure you don't go past the end of the list. So you could say, and p.next is not equal to null, in case it's not in there. You want to stop it. Then when that finishes, you need to know whether it finished because the target is in the next node or because you ran out of nodes. So that's one if statement. And then based on that, you can rearrange using this sort of step two sort of thing here, right? So, which is actually quite simple. Does that help?